All right, everybody. Well, I hope you're doing well. Welcome back to Environmental Restoration, and I hope you've had an awesome weekend. So we're going to talk a little bit more about wetlands today, but I just wanted to review briefly and make sure that those of you watching this video received the email from the provost about our updated grading system. So essentially this semester you all will have the option to decide whether you want a letter grade, pass, fail, or even to withdraw from your class up to 2 weeks after final grades are posted. So any grade that you take as pass, fail will not count towards your GPA, so that's one thing to keep in mind. So we described wetlands the other day, and I hope you had a chance to watch the videos on wetland delineation to really get an idea of how we define wetlands legally, which is an important thing to do under the Clean Water Act. So I want to talk today a little bit about why wetlands are important, and then about how wetlands have been degraded before getting into the restoration practices next lecture. So this is a study that looked at how much it would cost if we were to do ourselves the things that ecosystems do for us naturally. So it looks at ecosystem services and how much it would cost if we had to do this essentially in the lab or mechanically or whatever. And so this author, Robert Costanza, looked at different biomes and then what their primary ecosystem service was, about what value they provide per hectare due to that ecosystem service. And then he summed it up by multiplying the value per hectare times the total number of hectares of that particular ecosystem on the planet. And I think it's informative from a wetlands perspective because we look at those that have the highest value per hectare. Several of them are wetlands, so estuaries where rivers flow into the ocean, swamps as well, and tidal marshes are all different kinds of wetlands. And when you look at their total value per hectare, very, very high. So nutrient cycling is really important. Also, regulating disturbance. So when storms come in, these wetlands act like a natural sponge. And so they soak up water when there's too much water coming into the ecosystem. Similarly, they provide a reservoir of water when you're in the midst of a drought. So this is an interesting study. One of the take-homes from it is that when we sum up the total global value of all these ecosystems is greater than our global GDP. So the short answer is we as a society could not afford to do the ecosystem services that these natural areas are already providing. But then from a wetland perspective, it just highlights how important these are to ecosystem services all over the globe. And very important for lots of species as well. Many migratory bird species are obligate wetland breeders. That means they have to have wetlands to breed. And then there are many species which are facultative wetland species, right, which come in and use wetlands from time to time throughout their life cycle. So lots and lots of important species are dependent on these wetlands. All right, so these wetlands definitely have value, but they're ecosystems that are in bad shape for a lot of reasons, and I want to describe a little bit about their rarity. So if we break it down state by state, states like California and Ohio have lost over 90% of the wetlands that they had back before the 19th century. So if we find North Carolina in here, we've lost about half of our wetlands. But the point is that as a whole, we have a lot less wetlands in the U.S. So in the U.S., we've lost total more than half of our wetland. And the primary reason for this loss has been agriculture, because we wanted to come in and plant crops in areas that have been wet, right? Because the nutrient cycling we mentioned earlier, really important. So high nutrient content in wetland soils, right? Because it's not able to decompose. Remember that black color in our soil, that's organic matter that's still sitting there, and it makes these soils very rich. But clearly we can't have areas flooding that we're trying to grow crops on. So It's estimated that about 90% of the loss of wetlands in the U.S. has been due to draining for agricultural purposes. There was a time when people could canoe from central Illinois all the way to Chicago. It was kind of one continuous wetland. Now it's all been drained and it's agricultural land. So the loss of wetlands is significant in North America. Our ecosystems now look a lot different than they used to. Now, one of the ways that that's done is through the use of drainage tiles. It's a little cartoon on the upper left. Shows you how this works. So basically what you do is you bury these tiles, or pipes are essentially what they are, and they're perforated. So what happens is, as the water level starts to rise in the soil, the water collects in these pipes or tiles and then flows out. And what you do then is you dig a ditch along the edge of the field, and these drainage tiles allow the water to move out to that ditch, and you can drop the water table far enough down that there's enough of a zone to plant crops of different kinds. And so this is the easiest way to drain a wetland. You dig these ditches and then install these drainage tiles. All right, well, what does that look like in our neck of the woods? So I had a couple of research students that were working on land use and land cover in the Upper French Broad River watershed. And so I'm a stream guy, and so I think geographically in terms of watersheds. So all of us in the Upper French Broad River watershed right now, right, and it flows on down into the Nolichucky, Tennessee, Ohio, Mississippi, and ultimately the Gulf of Mexico. But this is where we are. So let's talk a little bit about the wetlands story where we are, and something that we found out as we started investigating land use and the history of it in our area. So the first thing that's pretty cool is that this Upper French Broad River watershed has many smaller watersheds. So you're familiar with some of these. So the cartoon there that we made on the right, Swannanoa River is in Asheville, as is Hominy Creek. So Asheville's about halfway up that cartoon. If you go up to the north, you see Reams Creek, Flat Creek, Ivy River, Big Laurel. On the east side, on the west side, we've got Newfound Creek, Sandy Mush, Spring Creek. Then to the south, we've got King Creek, Mud Creek, the Little River, the headwaters of the French Broad at Rosman, and the Davidson River, and the Mills River. And if we look at what land is used for in each of these watersheds, there are a lot of stories here. So this is percentage of each category of developed land that's urbanized, basically, based on the percentage of impermeable surface. Percent that's agriculture, percent that's deciduous forest, and then any other least developed category, right? So this could be certainly evergreen forest. And just glancing at those columns, one thing that might jump out at you is that a lot of those watersheds are primarily deciduous forest. That's the case for the majority of them, but not all. You can see, for instance, Flat Creek, right, is only about 37% deciduous. Mud Creek, only about 30. So I want to take a closer look at Mud Creek. It's the only smaller watershed in the Upper French Broad that has over 30% developed. On top of that, it has the second most amount of agriculture use at 21. So you can see it's over half either developed or agriculture. So it's a watershed that's been greatly impacted by people. If you look at the watershed again from an elevational perspective, I like this view because it kind of gives us the large-scale lay of the land, right? So you can see Asheville in the center there. Those blue polygons are urban areas. So Hendersonville is down there to the lower right. In Hendersonville, the Mud Creek watershed is located, and so you can see there's a little bit of mountain up there, a little bit of hill up there to the northeast, but really Mud Creek itself is kind of a sprawling watershed on a pretty flat area of the Upper French Broad. So as part of this project, we had to trace the flow patterns of streams And we did that to measure what the land use was like right along the stream in the riparian zone. So as part of doing that, we had to overlay in ArcMap these aerial photos with computer-generated stream files. Then we had to go in and correct them. So we did a lot of kind of what's called digitizing, essentially, right? We were tracing these along. And as we did this, we started noticing so many places in this Mud Creek watershed where there were strange shapes to the watershed, to the streams. These straight lines, which natural streams don't flow in straight lines at all. So when you see straight lines, it tells you that people have done something to those channels. So here you can see a larger stream flowing through the center and coming down from the north, a straight channel, and then down just a little bit below, you can see two straight channels. That, again, here's another example, a strange-looking stream flow pattern. So you can see the stream that comes in from the upper right doesn't have any kind of meandering pattern at all. It's just a straight shot. That's most definitely been channelized. And we see these two weird parallel straight lines, stream shapes in the center there. And so these have definitely been dug to drain wetlands. And so when you see this kind of a pattern, that tells you that there's been a lot of wetland drainage that's happened. If we zoom in a little bit, it looks like this. So there's Mud Creek to the right, and then this channelized ditch to the left. Interestingly enough, there's a very big restoration project currently going on where Mud Creek meets the French Broad River. And so we'll talk a little bit about that in our next lecture, but suffice to say, this is a watershed that used to have a lot of wetlands on it that doesn't anymore, and it affects the way that the ecosystem works in all sorts of different ways. And you can just see from this aerial picture all of the agricultural land use going on around it. And you can see again a couple straight line streams, and so that tells you again channelization and drainage has been going on. Okay, well, if you think of other things that we've done to the landscape that have affected wetlands, you might remember from last time talking about dams, right? All of these dams, over 70,000 cataloged, quite a bit more. But each of these dams is going to affect the flow of water and sediment. And because of that, it's going to affect wetlands. Here's a picture from Nepal. This is an Asian one-horned rhino at a national park near where I was in the Peace Corps, coming to check out a wetland. These rhinos are huge. They're up over 5,000 pounds they can weigh. And so this wetland that it's checking out here is a seasonal wetland. The monsoon plays a big role in the ecosystem out here. So this is a seasonal wetland that the water is only saturated up until the hot season starts before the monsoon, and then it dries down. But these rhinos and a lot of other wildlife really need these areas. Where you'd most often see rhinos are in the grasslands like here, and you know, this is kind of the equivalent of the American Midwest out in Asia climate-wise, and so you've got the large herbivores just like we used to have the buffalo. Okay, so this is an article that blew my mind that came in the journal Science in 2008. So, in the eastern U.S., dam construction really started in the 1600s. This is technology that began in Europe in the 1100s, and when folks came to the U.S., they brought the technology with them. Now, before the steam engine was invented, every mill that was doing work needed a dam to create a water pressure that would turn a wheel. This is a picture of a mill built fairly late in the game, in late 19th century in Catawba County. So these things were everywhere. So by 1840, over 65,000 of these mills were built, and you know, all across. Right, there aren't too many white counties where the color white in this graphic are counties that did not have mills. So these mills were everywhere on our landscape all of a sudden. So we think of the environmental effects of these dams. They're going to reduce flow velocity. So you're slowing down the water. So as much as 60% upstream. And when you slow down that water, it's going to allow sediment to settle out. So a lot of sediment was trapped upstream of these dams that would normally continue flowing downstream. So these authors took a close look at Pennsylvania, where there were over 1,000 dams constructed, and typically every 2.5 to 5 kilometers. So pretty close to one another. But the interesting thing is now that over half of those dams are breached. So that means they've broken and the water has flowed over them. So if you've ever seen a river or stream with a bank that looks like this, you might wonder how it got that way. This is what's called an incised stream. In other words, it's literally dug down into the land. But what these authors figured out from taking core samples and just observing the way that streams had cut through the soil was that if you can see that dark stripe right near the water level, it's kind of below that lighter brown layer of soil, that was actually a wetland that was in existence after the glaciers moved north, right? So newer than 15,000 years ago. So they started wondering about this, and it looks like this as well. Now, if you remember from last week, those dark colors result from organic matter that hasn't been broken down, right? There's no oxidation to turn that iron and other chemicals into that red iron oxides and others. So when you see that dark stripe, you think of soil that has been submerged. And so seeing that dark soil told these authors there was a wetland that had been buried. So here's what they figured out. They looked at the soil, and one thing that happened with all these dams on the landscape is that over time the ponds would get small as more and more silt was deposited behind them. And so ultimately those ponds would actually turn into swamps. And so these riparian forests had only been around since about 1850 or so, because they found trees that were greater than 100 years old, but not a lot. And so what this tells them is that the forests along these streams became established after there had been all this sedimentation behind the dams. And that forest was established on top of essentially this wetland. So, based on their studies, what these watersheds were like back before people settled, back before Europeans settled, was that we had these broad forested wetlands with shallow streams that flooded pretty frequently. And the reason that they concluded that was because when they took these core samples, when they got down deep enough, they found fragments of plants and seeds that indicated wetland species, both obligate and facultative. Okay, so how did we get things to look the way that they do now, though, you might ask? So after the steam engine was invented, these mills were abandoned. They weren't needed anymore. So eventually they breached, they broke down, and when they broke down, that water would rush downstream. As that water rushed downstream, it would cut into that wetland that was created above the next dam, and that would create this incised bank. That would erode down into the wetland and create the stream channel. So what they concluded is that these meandering stream patterns, which we see so much of, especially in the eastern United States, is not the natural state of these streams. That what was much more natural was a wetland where a stream and river would rise to access its floodplain frequently. But that the reason it looks this way now is because we've had breakdown of these dams and erosion downstream to create these incised channels. And this connects with historical accounts that our rivers and streams in the eastern U.S. was a lot more like a wetland than anything else. I mentioned before, out in the Midwest, you could actually canoe from central Illinois to Chicago because wetlands were much more common. Here in the eastern U.S., again, they went away partly because of these dams and their subsequent failing. So I think one of the takeaways, wetlands are just not good ecosystems for people to live alongside. We drain them when we want to grow crops. We also drain them when we want to develop by putting impermeable surfaces down. And so for all different reasons, we've lost quite a few of them. But there have been some other reasons as well that we've lost wetlands. There have been some cases where overgrazing of livestock has been a problem. It can lead to erosion when plants are grazed all the way down. And then also addition of nutrients or toxins. These are things that have essentially reduced the quality of wetlands, so that when you get that kind of eutrophication through nutrient input, the species aren't able to live there that were able to before, and so the wetland isn't able to function like a natural wetland would. The final threat to wetlands right now is climate change. So it's estimated that a half-meter rise in sea level would result in the loss of a little over a third of our coastal marshes in the contiguous U.S. And so the current rate of sea level rise is about 4 millimeters a year. So if you do the math, half a meter, right, would be 500 millimeters. So, you know, we'd be looking at, so this rate, of course, has been accelerating. But if we were to take 5 millimeters per year, let's do the math here, that would be about 100 years. Right. So anyway, so if that's the rise that occurs, we lose about a third of our coastal marshes in this particular area. So climate change is a final issue that is threatening our wetlands. So wetlands, crucial importance to us from an ecosystem services perspective, from a wildlife habitat perspective, but unfortunately our use of those areas for agriculture, as well as some other historical land use considerations, have resulted in the U.S. having about half the amount of wetlands that it used to have, and in some areas some pretty extreme loss, particularly areas that are experiencing high rates of agricultural land use. So our next lecture is going to talk specifically about how we start restoring these wetlands, and I will talk to you then.